our session of AMA for Physicochemical Factor for FAR 323. Let us look at a question that posted by your friends. So the first question say, "Hi Dr. Chan, can you explain more about dissolution as rate limiting step and absorption as rate limiting step?" Okay, when we talk about rate limiting step, means that we are talking about the whole process of a drug being into your body and take its effects. Okay, so the whole process to take effects, where is limiting this effect to take place? Okay, there are two different steps that can limit the step of effectiveness, which is dissolution and absorption. Okay, for a drug that is poorly soluble, very poorly soluble, and the dissolution can be very slow, right? When it becomes very slow, then dissolution will be the rate limiting step. Okay, but however, for a drug that is a highly soluble, okay, let's say paracetamol is highly soluble, so it is dissolution do not have any problem. Once you put into the water, then it will dissolute, meaning that what you have seen in your coffee powder, it will dissolute very fast. And then where is the absorption rate if the action still did not take place? Okay, then we will start to suspect absorption is the rate limiting step. Okay, in terms of absorption as a rate limiting step, there are a few factors that can cause absorption to be rate limiting step. For example, you need a certain receptor to get absorbed, okay, and the drug molecule is very hydrophilic, and it is not compatible to your lipid bilayer, so that it cannot easily penetrate. That is rate limiting step. Another one is maybe they are highly metabolized by the first pass metabolism by PGP and CYP3A4. That can also be a cause of absorption as rate limiting step. Okay, but when you have a poorly soluble drugs, okay, so dissolution usually is the rate limiting step. So what a formulation scientist like me to work on it is trying to increase the dissolution rate, so to get rid of this as a rate limiting step. Okay, then we will leave it for absorption. All right, so this is about the dissolution as rate limiting step or absorption as rate limiting step. Next question. So doctor, I want to clarify that the higher dissolution rate, it can be absorbed faster, and that's why it is going to achieve high bioavailability. Is that right? Because a lot of drug can enter the bloodstream faster. Okay, now pertaining to this question, for this particular student, when you talk about this faster, meaning that you are comparing with something. Okay, you are comparing with something. Okay, so now if you are saying if you have higher dissolution rate, again you compare with something. Let's say I have something A and something B. Okay, the dissolution rate is 10, for example A, and dissolution rate of B is 20. Of course, I will get a higher bioavailability for B. Am I right? I mean, that is a straightforward thinking. We don't talk about whether it has the extent of absorption. Is it higher or is it slower? At least when you have the beginning phase, which is the higher dissolution rate, you will start to expect it is going to have higher bioavailability. But that is when we talk only about dissolution, okay, because we did not know about absorption. Okay, so say I want to clarify that the higher dissolution rate, it can be absorbed faster. Okay, a higher dissolution rate can facilitate absorption. Okay, it can facilitate absorption. Whether or not it will entirely make the whole absorption faster, it is very much dependent to which drug are you talking about. Okay, let's say the drug, let's say for this A and B, they are the same drugs. Of course, in a comparable manner, when you have B being higher dissolution rate, of course I will expect B to have higher bioavailability, and that's all. That should be comparable. But if you're talking about something not comparable, apple to an orange, then of course you will need to depend on what type of drug are you talking about. Okay, and you say because there are a lot of drugs that can enter the bloodstream faster. Yeah, okay. as you know, drug can be divided into bio-classification system, that the drug can enter the bloodstream faster, usually class 1, okay, BCS class 1, high dissolubility and high permeability, and class 2 is low solubility, high permeability. Still, if you increase the dissolution, it can reach the bloodstream very fast, okay. However, class 3, when you have low permeability, and the class 4, when you have low permeability, would it be the same? It is very much dependent to the different type of drugs. All right, next question. So doctor, for the dissolution of a drugs, if a drug is in a salt form, its dissolution will increase due to the higher aqueous solubility. Correct, yes. Okay, since the absorption increases with more uncharged particles, which is more lipophilic, how then to formulate the drugs? Okay, as I have mentioned in my lecture, when we talk about a dissolution of a drug in a salt form, okay, they will exist in equilibrium in this equation, okay. Okay, now pay attention, they will exist in equilibrium in this equation, okay. In this equation, which drugs will actually get absorbed is the unionized one, which is here, will get absorbed. So the unionized will get absorbed, okay. When the unionized get absorbed, according to this principle, when you have this one being consumed constantly, so the whole equation will go here, right, will go this way, okay. So be it the process of making it salt form, right, making it salt form, all right, you can facilitate dissolution, but don't worry, they will be going through the unionized form for absorption later on. It's just that they will facilitate the breaking of the big particle into small particles so that they can be ionized. Even though after they become ionized, they will easily, because of this weak acid and weak base conjugation of the formula, they will actually shift it to an unionized form in order for absorption. So in the net process, okay, net process, absorption still increase even though you have moved to the uncharged particles, okay. So meaning that there are two competing effects, okay. When you make into salt form, you will increase the dissolution, okay, and you will start to think, well, am I decrease the absorption because more being ionized? As I said, because the intestine has constantly consumed the one uncharged. So for this formula, they still function in a way that they will shift to the uncharged formula so that it can be absorbed by the intestine. So the net process, okay, the net process still increased. All right. So how then you formulate the drug? You can still formulate the drugs into a salt form if you like, right? But of course, you will offset by this uncharged form afterwards if you want to increase the absorptions. But that, as I said, that doesn't matter because in the net process is still increased. All right. So, hi doctor, is there any possibility of polymorphism in IV drugs? If possible, so what action do we need to prevent or improve the solubility of IV drugs? Okay, says now polymorphism is only happen to solid, okay, only happen to solid. Okay, let's say if you are talking about the IV solution that you have made, okay, with Dr. Go or whoever that teach you about the injectable, okay, those are pure solution. If you still remember, after you have done this IV solution, you will need to go and check the particulate, which is Allen viewer, right? You need to check what is the particle size, is there any particulate there, because in IV you are not allowed to have any foreign particle or impurities. Okay, now here comes the question, is there a possibility to inject IV suspension? Okay, actually there is a possibility to inject IV suspension, especially when it is nanoparticles, okay, nanoparticles. Okay, so some example is like paclitaxel, the anti-cancer drugs that you inject in IV suspension. There are a few advantages that you inject in IV suspension. For example, they can enhance this T-half, okay, you can circulate into your bloodstream for a longer time, okay, and also you get more stable, and because you reduce the solubilizing agent, okay, the toxicity can be reduced. Those are some of the benefit of IV suspensions. But you have to bear in mind what is the diameter of the lumen that you are going to inject for this IV suspension. So here I attached the table 1 for your reference. Okay, this paper is talking about these IV suspensions. So what do the action that do we need to prevent polymorphism? If you need to prevent polymorphism, okay, in a suspension, well, usually you will need to study in the course of the shelf life whether your formulation is stable. Okay, when you need to study whether a formulation is stable, you need to check about their, X-ray diffraction, whether or not they change from one form to another form. They will show different peaks, right? Those are this investigation that you need to check. And then you say what action to do to improve solubility of drugs. Okay, there are other action that you can improve solubility of drug. Let's say if you do not want to have suspension, then of course, or you want to reduce the particle, you can increase solubility by adding excipient. Okay, excipient. What type of excipient that actually can improve solubility of something that is initially not soluble? Initially not soluble becomes soluble. Okay, so what you can do is you can add actually kind of like surfactant. Okay, you can add a solubilizing agent. Okay, that is very much depend on what type of drug are you working on. I can give you like surfactant, you can add twin. Okay, you can also add chromophore. Chromophore is a solubilizing agent, but it is also a type of surfactants. Those are the things that you can actually try to add to improve solubility of IV drugs if they exist as a suspension. But strictly speaking, most of the IV, they exist as a solution, because when you need to use suspension, you will need to be extra careful, right? So let's look at the next question. So doctor, can you explain more about the drug in inclusion complex with cyclodextrin? The hydrophobic drug is put in hydrophobic core, okay, hydrophobic core, okay, not hydrophilic core, hydrophobic core of cyclodextrin in order to dissolve better in water and increase solubility of the drug. Yes, you are right. It is putting into the hydrophobic core, and the outer layer is hydrophilic, so that it can dissolve in a carrier of solvent. Okay, so hi doctor, can you explain about the inclusion complex with cyclodextrin? I couldn't understand because I'm unable to see the illustration since my cursor cannot be seen. Okay, I apologize for the cursor that you cannot see. So let's move into understanding this slide. So the same question has been asked by another student regarding the graph that you put under inclusion complex with cyclodextrin between alpha, beta, and gamma. Here we have the alpha, beta, and gamma. Does beta complex is more preferable, or it may change depend on type of the drugs? Of course, it may change depending on type of the drugs. But the drugs that I show in the example of the slide is actually artemisinin. Artemisinin. Artemisinin is a type of anti-malaria drugs. Okay, when they cannot encapsulate well, like this case, okay, they are not optimum enough. Okay, and when they can encapsulate, okay, this is good enough here, beta cyclodextrin. And when you use the gamma cyclodextrin, is a bigger one, and they can encapsulate the whole artemisinin. However, the release of artemisinin when the action is needed is not as optimum as the beta. So in this case, beta is the best. Okay, are we knowing in advance? No, we do not know in advance. We have to do a dissolution study, we have to do a bioavailability study or absorption study in order to understand which one will give you the best result, right? So here comes the next question, similar to this cyclodextrin. Hello doctor, can doctor explain how can we judge a dissolution profile? Which one has a good dissolution profile, which one is not? For example, between the beta and gamma cyclodextrin complex, which one is better? Okay, if you look at the dissolution profile here, okay, let's see, alpha is the pink color here. This one is alpha. Okay, beta is this one is beta. And gamma is this one. This is the gamma, right? So between gamma and beta, which one is better? Of course, alpha is out because it is dissolution, even though it's okay, but then the extent of release is not good, right? Between alpha and beta, what do you expect? Okay, alpha, that you got dissolution rate relatively higher as compared to beta in the initial phase. Okay, it released faster, right? Beta released slightly slower, but beta having a more consistent release afterwards. Okay, more consistent release afterwards. However, gamma, after some time, they release reduce. Okay, meaning that they only achieve a peak and then there is a reduction of parachuting shape, and that is inconsistent. Okay, of course you like something that is more consistent, and the inconsistent, if you don't want that to happen into your formulation, then that is not an optimum one. Of course we want to try to maintain the drug concentration in our bloodstream. Of course the consistent release is the best that we see, so beta has been determined to be slightly better than the gamma. All right, let's look at this next question. So similar to the previous question, in the video, doctor mentioned that drug dissolution profile can determine by looking at the Cmax and Tmax, right? Okay, drug dissolution profile can determine by looking at the Cmax and Tmax. And shorter Tmax will give us better bioavailability. Is it we can calculate the bioavailability using Cmax and Tmax? Okay, by now I believe that you know how to calculate the bioavailability or pharmacokinetic parameters Cmax, Tmax using whatever that Prof Yuen have teach you before. Okay, but anyway, this solution profile you can determine by looking at the Cmax and Tmax. Okay, Cmax is the maximum concentration achieved at the highest concentration of Tmax. Okay, now Tmax here for let's say beta is this one. Okay, Cmax is around more than 400. Okay, and the gamma Cmax is around 400. All right, and Tmax for beta is actually less than 1 hour, but for gamma is exactly 1 hour. Well, you can only estimate, you cannot really determine the real number, right? You can only estimate the one that is achieving higher Cmax at a shorter time. Of course, you will suspect they have a very good dissolution profile, right? The one that is having slightly longer time to achieve the Cmax, of course, you will suspect they have the dissolution profile that is slower, or dissolution rate that is slower, and that's all. You can only estimate, right? Okay. And is it we can calculate bioavailability using Cmax and Tmax? Bioavailability is actually area under the curve. Okay, if you know this here and you know here, okay, of course you can calculate the bioavailability by using area under the curve. Okay.